If you are anything like your TA Serenity, you probably hate the method of virtual work, but hopefully that's just because it's unfamiliar to you. But if I can get you to a point where you still hate it, but you at least think to yourself, well, at least I get why it's useful or why other people might like it, then that's my win condition, right? That's what I'm really trying for today. Because the alternative to virtual work is the thing you're very familiar with, which is drawing free body diagrams and sum of forces and sum of moments. You've been doing this since static. It's comfortable and familiar. But I want to really emphasize that virtual work is better for machinery problems than Newton's laws. And I've got a super quick mini lecture to explain what virtual work is, and then I'm going to explain when or why you might use it and why it's better, and then work through a full example problem so you can see every step along the way as to exactly how it works. So virtual work, think back to your dynamics class. Work was force times distance, and power was force times velocity. That's for objects that are translating. For objects rotating, they are torque times angle, or torque times angular velocity for power. And you would have seen this in your dynamics class in the conservation of energy section, because the change in energy in a system is the amount of work being added to the system or amount of work being done by the system. So for a machinery problem, what I want you to think of is this green drawing that I'm putting on top of this 4-bar linkage here, where imagine that the whole system rotates just a super tiny amount, just a couple degrees. When this system rotates, you'll see that each force will have pushed its point, like points B and D, will have moved by these little teeny tiny distances. And then the crank will also have rotated by an angle. And if there's a torque applied to that crank, then that torque is acting through that rotation angle of the crank. And the example problem that I'm going to do today is we are going to solve for the amount of torque that will hold this system in equilibrium against these two other opposing forces, PB and PD. And so naturally, this looks like, oh, draw some free body diagrams and some forces, right? That's the easy, obvious, brute force way to do it, but it's not the most elegant way. A way that's a little bit more refined, a little bit fancier, but it's a little bit more useful is virtual work, where we're going to use an energy method, and we're going to say that the amount of work added to this system from PB and PD, this force times distance, has to be offset by this torque times angle, because the change in energy of the system, delta U, has to equal the change in work of the system, delta W. And if the system is in static equilibrium, then delta U has to be 0, which means that all of these changes in work have to exactly cancel each other out. And so since we are given the forces and we want to find the torque, we can do that essentially if we're able to solve for these distances and angles. And this isn't super impossible to do. We could, in fact, just plug in like a little tiny 0.01 degree angle change and then find where these points B and D move to. We could actually find these distances. But the problem gets a little bit more tedious when you recognize this is not just straight multiplication, force times distance, it's force dot distance. It's a dot product. And this is because the amount of work being done is force times distance, but it's only the force in the direction of the distance. So since these forces are coming in at weird angles, part of the force is being wasted sort of in the direction of the pin, and only part of the force is in the direction actually causing rotation around the pin. So part of the force is wasted, and we have to find the component of the force that's pointed in sort of the tangential direction. All of the normal component of the force ends up being wasted, just kind of, again, applied at like 0.4 at the instantaneous center of rotation. And so the hardest part of virtual work problems is probably actually, it's sort of like the geometry, trigonometry of it, of finding these angles to use for the dot product so that we can get just the component of the force pointing in the direction that points B and D are actually moving. But now here's the real genius as to why virtual work is so valuable for evaluating mechanisms, is that if I take a time derivative of this equation and do torque times velocity, torque times angular velocity, and do, instead of force times distance, force times velocity of each point, right? Now essentially we're doing power instead of work. But what this does is this gives us velocity terms. And if we're analyzing a mechanism, it's pretty unlikely that we are only interested in solving for torque. Now, for a regular homework problem, that's all we're trying to find is torque. But if you were actually building this system and you actually wanted to analyze the motion, if you actually wanted to analyze the motion of this linkage, you would want to know position and velocity of each of these points. And so the great thing about virtual work is that you can solve for virtual work along the same pathway that you would already solve for velocity, so you don't have to do two totally separate steps. If you use Newton's laws and draw free body diagrams and sum forces, the only thing you will find is force. But if you do virtual work, not only will you solve for force, but you will also solve for velocity along the way. That is why virtual work is valuable. It lets you solve for more than one thing at a time. So your time is valuable. You want to solve for as much stuff as you can with as little effort as possible. That's what virtual work is. You solve for position and velocity and forces all at the same time. All right, maybe let's get to the example problem. So if I want to solve velocities, I'm not actually given any velocities. And in fact, this problem is going to be in static equilibrium, so none of them are actually moving. So what I'm really finding are kinematic coefficients. This is the velocity of each point or each link with respect to the input link, so that we could assign any input velocity to the crank we want and just do a simple multiplication step by this kinematic coefficient, just the ratio, and get the output velocity. And so the first step before finding linear velocities is going to be to find angular velocities. And I wrote this down as theta dot 3 and theta dot 4, which would be like radians per second. But actually what I want to find is theta prime 3 and theta prime 4, the kinematic coefficient, which is the velocity of link 3 and link 4 with respect to the input velocity of theta 2. And my final step to get the linear velocities is just going to be v equals r omega, which is the velocity b prime is equal to the radius from point B to its instantaneous center of zero velocity times theta 3 prime. V equals r omega. You've probably been using this a whole bunch of times if you've done like gears. If you did gear problems, you used v equals r omega a million times already. And I said the steps are going to be the same for virtual work as for finding position and velocity. And I'm going to use the loop closure method or the velocity loop method, where I'm following basically two paths here on my triangle. I'm going to follow the crank and coupler, so from O2 to A to C. And then separately, I'm going to follow ground and the rocker, so from O2 to O4 up to C. I'm going to say that these two paths, since they start at the same place and end at the same place, these two paths have to sum up to the same value. That's loop closure, velocity loop method, vector loop method. So in the x direction, 4 cosine theta 2 plus 10 cosine theta 3 is equal to 8 plus 8 cosine theta 4. Y direction, just replace cosine with sine. 4 sine theta 2 plus 10 sine theta 3 is equal to 0 plus 8 sine theta 4. For my derivatives, since I'm going for kinematic coefficients, and since I don't actually know any speeds, right, I'm taking a derivative of both of these equations with respect to theta 2. Again, this is going to make my derivatives a prime. I'm going to call that a prime instead of a dot. A dot would be a time derivative. Prime is a derivative with respect to something else, in this case, theta 2, the angle. So derivative of 4 cosine theta 2 will just be negative 4 sine theta 2. And the derivative of theta 2 with respect to theta 2, right, is just 1. It's itself. But for the next one, derivative would be negative 10 sine theta 3 times theta 3 prime. This is because of the chain rule. When you take the derivative of cosine theta 3 itself is a function of theta 2. So you have to take the derivative of it also and kind of move that outside. Chain rule. Is equal to 0 plus negative 8 sine theta 4 prime. And this will be kind of weird. Again, if you're not super comfortable with kinematic coefficients, you may want to go watch another video on kinematic coefficients where, I've got one on my playlist, but you can actually get more explanation of exactly what these terms mean and more practice doing these types of derivatives, which are not the hardest you'll ever see, but they're a little bit unusual. So same derivative in the y direction, the sines become cosine, and then we've got, again, theta 3 prime and theta 4 prime are kind of popping out, again, because of the chain rule. And so right now I've got 5 unknowns, right? Theta 2, theta 3, theta 4, and then theta 3 prime, theta 4 prime in this equation. But if I can find these 3 angles, which I should be able to find, if I can find those 3 angles, then I'll only have 2 unknowns. I'll have 2 equations and 2 unknowns, where I'm looking at my 2 equations of these 2 blue ones, these equations for the derivatives with velocities. And I'll be able to actually solve for these kinematic coefficients, theta 3 prime and theta 4 prime. All right, well, so theta 2 is given, right? That was right on the drawing from the very beginning, 180 degrees. And maybe you just wrote in 180. You didn't have to write in theta 2 from the beginning. So now we're looking for theta 3 and theta 4. And as is basically always the case with mechanisms problems, solving angles is going to require law of cosines. You probably thought after your first couple of years in college of not seeing law of sines, law of cosines very much that you were done with that part of your life. But then when this class came along, you've probably done at least 100 law of cosines by this point in the semester. So hopefully this is actually gonna work out for you, not too bad. So first start off solving for theta 3, where 8 is the opposite side, so the 8's by itself, and then the 10 and the 12 are the 2 adjacent sides, so they're on the same side as the cosine. Get theta 3, 41.41 degrees. And then for theta 4, we can do the same process, except now the 10 is the opposite side, so 10 is by itself. But we do have to be a little bit tricky in that theta 4 is actually the angle outside of this triangle. By convention, we usually put theta 4 again over there with respect to the x-axis. And so I have to solve for cosine 180 minus theta 4, because that's the angle inside the triangle, would be 180 minus theta 4. Get a final answer here, theta 4, 124.23 degrees. And now we're just solving a linear equation. It's just 2 simultaneous equations, the 2 blue equations there for theta prime 3 and theta prime 4. Man, what a tongue twister. Theta prime 3, theta 3. So the first 2 by 2 matrix is just going to be the coefficients of the theta 3 and theta 4 terms. Theta prime 3 and 4 are going to be a vertical, just a 2 by 1 matrix. And then that last vector on the equals is going to be the separate, independent, just numbers. The one that had theta 2 in it, that's just a number at this point. There's not even any variables because theta 2 was known, 180 degrees. So a little bit of calculator first to simplify this out. A negative 6.6, positive 6.6, positive 7.5, and 4.5 is equal to 0 and 4. And I punch this into my calculator. I've got a TI 36X Pro, which can actually solve 2 by 2s. I just type in all these coefficients, get that theta prime 3 and 4 are actually both equal to each other, both 0.3333, just 1/3. And just at a super quick check, you can see, yeah, 1/3 of 7.5 is 2.5. A third of 4.5 is 1.5. 2.5 plus 1.5 is 4. Okay, yeah. So like I said, that does work out. And it seems like we're actually making some pretty good progress here. If we can just find these radiuses, the distance, right? V equals R omega. This will allow us to actually get the velocity terms that we need for that torque equation, right? The conservation of energy equation from the very beginning. Well, the first one, D is just, it's attached to the rocker. It's just pinned about 0.04. So the radius from D to its instantaneous center is the pin at 04. It's just the distance 6. So our DIC was given 6 by inspection. All right, why can't they all be this easy? The next piece of good news is that I happened to choose a problem where the crank was exactly at 180 degrees. So if I trace these two like dotted line sort of vectors back as to the directions for points A and point C, you can see that the instantaneous center right now for this coupler link is actually also at point 04. So that's going to make this problem a lot easier. I don't have to do more law of cosines and law of sines to try to find where the instantaneous center is. I can just go ahead and redraw this triangle where I've got 12 on the base, 14 on one side, and our BIC on the other side, where our BIC is just the distance from B to 04, which is the instantaneous center because, again, point A is moving straight downwards and point C is moving down at an angle, right? We can trace those 90-degree lines from those points, those cross at the instantaneous center. Now we've already found theta 3, which is the angle between the horizontal up to point C. But to get the angle all the way up to B, we need to additionally solve for the small angle, which I'll call theta BAC, right, which is inside that triangle. So this will be a law of cosines, your favorite law of trigonometry. So in this case, 5 is the opposite side, 14 and 10 are the two adjacent sides, and we get 14.57 for this theta BAC. And then we can solve for our BIC, the distance from B to 04, using law of cosines. So our BIC is the sort of opposite side of the angle, 12 and 14 are the two adjacent sides, and then the interior angle for this orange triangle is the sum of both, the 14.57 plus the 46.41 that was theta 3. 41.41. Get a distance here, 12.33 as the radius from B to 04. In order to find the angle in between the velocity of B and the force at B, I am going to need this extra angle we're calling here phi4. Now remember, in our final equation, there's a dot product, and we need to know the angle between the velocity of the point and the force at that point. So we are going to need this angle, which I'm drawing here in blue, that is phi b. And now that we know all three sides of this orange triangle, it's just another law of cosines. And 14 is the opposite side, 12 and the 12.33 are the two adjacent sides. We get phi b 70.34 degrees. And so if this angle at the bottom is 70.34, then the angle above, this is opposite interior angles, I think is the math name for this, is also 70.34. And since VB is at a 90-degree angle from our BIC, we can find this new value phi is just 90 minus this 70.34. And so the angle in between the velocity vector and the force vector is going to be 19.76 degrees. We're going to have to do this one more time for point D. We also need the angle between the force vector at D and the velocity of point D. So we had theta 4, which is that 124 degrees, but that wasn't up to point D. That's the angle up to point C. So in order to get theta D, we need to subtract the angle inside this triangle, the CO4D triangle. We need that small angle in there, which we can get by law of cosines for the millionth time. 4 is the opposite side, and 6 and 8 are the two adjacent sides. So we get this 28.96 degrees is inside that triangle. So we subtract that from theta 4 to get theta D, 95.27 degrees. So since the force at B is pointing upwards at a 30-degree angle, and then the velocity of D is kind of pointing downwards at about a 5-degree angle, then that means the angle in between those two is going to be about this 35 degrees angle in between the force and the velocity at point D. So I'm going to be projecting the force onto this direction of velocity using cosine of this angle. And we're almost there. We're really getting close. Right, so I've got a new clean drawing over here because I've been drawing all over the other drawings. So we've got VB and VD. They're both kind of pointing down. We've got our FB pointing to the left and our FD pointing kind of upwards. And so what we're going to be doing is projecting these force vectors onto a vector in the direction of VB, right? That's this dot product, because part of the force at D is pointing in the direction of VD, the tangential direction, but part of the force is pointing like upwards, just trying to lift the rocker out of the pin at 04. And that is not adding work to the system. That's just totally wasted force. We only want the direction of the force in the direction of the tangential direction, in the direction of the velocity. My power equation is written in terms of time, right, as a time derivative. So if I actually take the derivative of this with respect to theta 2, right, to turn this into kinematic coefficient form instead of time form, right, that's where I get these VB prime and VD prime terms. All right, so this dot product, P dot V, I'm going to rewrite as P cosine theta, right? This is, we're taking the force only in the direction of the velocity, so P cosine theta, that gets rid of the dot product. And then V is being rewritten as R theta prime, right? Like V equals R omega. So P cosine theta, R theta prime. And we plug in all the numbers and get to a final answer, 758 pound-inches. You could call it inch-pounds if you want. And so the awesome thing about this virtual work method is that we solved for kinematic coefficients along the way, so that now, if we wanted to solve for velocities for this mechanism next, we already have that work totally done, and we could give any input velocity for the crank and solve for the output velocity of any of the other two links, or points B and points D. We could get the velocities of those points basically instantly now with all of the work we've already done finding virtual work. If this video helped you learn something, click on the description below because I have a full playlist of mechanisms videos. Go ahead and click on the playlist. You're not going to watch them all right now, but just bookmark it. That way later on, when you have trouble with another mechanisms videos, you can just jump back to your bookmarks and find another one of my videos that's going to help you out with whatever your next homework question is.